Well, the remaining topics are Fourier transform, infrared spectroscopy, and the noise handling, right? And this section is also extremely important. Okay, modern infrared spectrophotometer now adapts Fourier transform principle. Okay, so that is called Fourier transform infrared spectroscopy. Now, ordinary IR spectrophotometer is based on dispersive principle. You know, like like in the UV or visible spectrophotometer, people use IR light source, yeah, and then using the grating for IR region, and then the monochromatized light is sent to the samples. Okay, so it takes a rather long time. Okay, and by scanning the wavelengths, you detect, you collect the IR spectrum. But completely different technique, so-called Fourier transform infrared spectroscopy has been developed, right? It has many advantages. Okay, yeah, and but understanding the principle is not easy at all. Okay, but anyway, let's learn. Yeah, at the level of undergraduate the studies. All right. Why FTIR? There are at least one, two, three advantages of FTIR. Okay, and then I already explained the weakness of dispersible spectrophotometers. Okay, when you understand the advantages of FTIR, you will know that this technique, FTIR in short, okay, is really superior to dispersible spectrometers. Okay, okay, yeah, let's start. So, the modern infrared spectrometer is, I think, almost, I think maybe all of them are based on Fourier transform, the principle. Okay, what are the advantages of FTIR? Uh, Largely, there are three advantages. First advantage is Felget advantage. Another name is multiplex advantage. Okay, multiplex advantage. Okay, or maybe you can remember the name by Felget. Okay, many scans can be completed and averaged on an FTIR in a short time. Okay, you see, in a dispositive instrument, you scan one by one. Yeah, but here you don't have to scan. Multiplex means the many one, many things, many at the same time. Mm. So since you scan many times, okay, and then you can, because one scan takes a very little time, sometimes less than 1 second, right? And then many scans can be averaged on FTIR in a shorter time. Let's see, one scan completes within 1 second. Okay, 100 scan takes only 100 seconds. Okay, that's the uh, one scan for dispersible spec dispersive instrument. Okay, and then when you have many scans, and then you simply add up to minimize the noise. Okay, that's the called the Felget advantage, and uh, the next advantage is called Jacquino advantage. Another name is throughput advantage. Yeah? With FTIR instrument, the high throughput can be obtained, yeah, with FTIR device compared with traditional spectrometers that need slits to achieve resolution. Okay? In ordinary spectrophotometer, there is a slit and also gratings and exit slit, yeah, entrance slit and exit slit, and after dispersive, uh, uh, yeah, the after through after the monochromaton. Yeah. So actually, the light intensity entering the sample is very weak. Okay, that's the low throughput. High throughput, yeah, Jacquino advantage is the high throughput advantage because instead of you monochromatizing the light, you send whole IR beam to the sample. Okay, so that's why uh, we are dealing with whole intensity. Okay, at the same time, that is called the Jacquino advantage, and the less advantage is called Kong advantage. Another name is wavelength accuracy advantage. Okay, in dispersive instrument, yeah, how precisely, however precisely you make the instrument, there is a error in wavelengths, but in FTIR the wavelength is calibrated by laser beam, okay, of known wavelengths. Okay? So the the resolution is absolutely high, you know. That's the Gong advantage, okay, since the instrument is calibrated by a laser, okay. Yeah, that's the another advantage. So it has at least three advantages, okay. But let's understand the principle of Fourier. You know, the Fourier is the name of the French mathematician, okay. He contributed to the mathematics a lot. One of his greatest contribution is that Fourier analysis. The Fourier analysis is what? He proved that any curve is decomposed into a sum of sine and cosine terms. That is called Fourier series. Okay. For example, you see, um, so by combination of sine and cosine, waves with different, the frequency, it is possible to construct any wave. All right, any wave. Here, look at that. Uh, this one, this is the solid line is actual, your spectrum, and then you want to represent, you want to, decompose this your data into sine and cosine functions with different frequencies. Okay, it is possible. The Fourier already proved this principle. For example, here the upper one. Let's see. In this case, n is 0, 1, 2. Okay, and it's 0, 1, and 2. This table shows, here how many n, how many cosine and cosine functions you need. Okay, and let's see. When you use this one and 0 and 1 2, in that case an is the coefficient, okay, given here. you you used only the first three data, and then you can synthesize this dotted blue curve. Okay, but this dotted blue curve is not does not resemble this real data, right? And then now increase, the n number down to 4. Okay, here 1, 2, 3, 4, 5. You used this 5 data. Okay, and then you synthesize it again, and then you saw this blue dotted line. Now it becomes resembling this original this black line. Okay, but still there are not much difference here. And then when you took all these 8, yeah, then this final conclusion is the blue dotted line and the solid line, they match very nicely. Of course, if you take more n numbers, 9, 10, 11, 12, yeah, more and more more and more n values gives you more much much more precise, yeah, the representation of the original spectrum. Okay, in other words, that this means that once you have this original spectrum, and then it can be decomposed into each one, or if we, when by combining all the sine and cosine, and then you can synthesize, this original uh, the spectrum. Okay, that's the Fourier analysis. All right.